Okay guys, so in the last video what we did was we played with Clifford algebra. We introduced it kind of, and we saw some properties of the gamma matrices, and we learned about Weyl and Dirac representation. In this video what we are going to do is we are going to derive the Dirac equation after constructing the Lagrangian based on what properties we want. Okay, so of course the first property for the Lagrangian is that it must be a Lorentz scalar, right? So the action remains Lorentz invariant. And the second is that, let me just the first one we all know is it must be a Lorentz scalar. The second one, which was Dirac's requirement, is it must be first order. Okay, unlike the second order Lagrangian of the Klein-Gordon equation. Okay, so this must be first order in derivatives. Okay, and must give the Dirac equation. Of course, we have the Euler-Lagrange equation, and it must be real. So the Hamiltonian is Hermitian. Okay, so these are our requirements, and just keep in mind that now we have psi, which is a complex 4-component object. Which means that it has 8 independent degrees of freedom. 8 real degrees of freedom, right? So just keep that in mind. So the objects that we can vary are psi, okay, and another object which we define as psi bar, which is the complex conjugate of psi multiplied by the temporal gamma matrix, if you want to call it that. Okay, and both of these will be treated as independent fields, independent variables. Okay, so just keep this in mind, psi bar. I think that might be a new thing. Okay, now what we can do is we can consider the terms that we can construct from these two, which are scalars. Okay, and I think we did this in a workshop and also I think or an assignment. I'm not sure which one, but we did do this in our assignments. And just go and please visit those assignments to see that the only objects that we can construct, or if you recall Lorentz invariant bilinears we can construct from psi and psi bar, which are also first order, okay, are psi bar psi, okay, psi bar gamma mu psi, okay, or psi bar gamma mu partial mu psi. Okay, these are the only bilinears that we can construct from psi and psi bar, which are first order. Okay, and here this quantity, as we can see, is a scalar. This is a 4 vector, but this is also scalar because it's contracted. Okay, and from this point on, so we can use this and this in our Lagrangian, but not this. Okay, because it's a 4 vector and therefore it transforms as a 4 vector. So this finally tells us the Lagrangian that we would need, and that is we put psi bar here and we introduce an iota, okay, to make sure that the Lagrangian remains real. Okay, gamma mu partial mu minus m psi. This is your Dirac Lagrangian. Okay, so this is your Dirac Lagrangian, and now we just go ahead and use the Euler-Lagrange equations to find the Dirac equation for it. Okay, remember that our independent degrees of freedom are psi and psi bar. Okay, so we treat them as independent fields. So just recall that the Euler-Lagrange field equations are given by phi I minus partial mu partial L or partial mu phi I is equals to 0. Okay, so let's just go ahead and first of all find the equation with respect to psi, okay, by varying psi. And if we do that, we get partial L over partial psi is equals to, so what we get is we simply derivate this, and in place of this we simply get a 1, right? So what we end up with, let me just make sure that I'm doing this right. Okay, so if I vary this with respect to psi, then okay, yeah, so if I vary this with respect to psi, let me just write this down, so because I was getting confused here. Iota gamma mu partial mu psi, this is partial mu psi actually and not psi, and then I have m psi, psi bar m psi. Okay, now this term vanishes because it has a partial mu with it, but this term survives, so I get minus partial psi bar m. Okay, and if I vary it with respect to the if I now find this quantity, okay, so let's just go ahead and find it. You will get partial L partial mu phi I, psi. Okay, and you can do this too, so let's just go ahead, and this quantity vanishes. Okay, this one vanishes, but this one survives, and I get iota psi bar gamma mu. Okay, and if you put this into the Euler-Lagrange equations, you can see we simply get, let me just write this down here, minus psi bar m minus iota partial mu psi bar gamma mu is equals to 0. Okay, which upon rearrangement gives you psi bar iota gamma mu partial mu but applied to this side, okay, plus m is equals to 0. Okay, this is your Dirac equation. Actually it's the conjugate Dirac equation. Okay, and you can find the Dirac equation by varying the Lagrangian with respect to psi bar, while I did it with respect to psi. Okay, and when you do that, you will find that the Dirac equation is iota gamma mu partial mu minus m with respect to psi equals to 0. So this is the beautiful Dirac equation, and later on we will also verify that the square of this equation gives you the Klein-Gordon equation. Okay, so right now what we are going to do is just write the Dirac equation in explicit form to get some perspective, okay, and also some practice with it and some intuition for it. So this is the Dirac equation. Now if we expand it, what do we get? Well, let's just expand the first part, of course, because there is nothing to expand in the second part. Okay, so if we expand it, we get iota gamma naught partial naught minus iota gamma 1 plus gamma 1 gamma I gamma I partial I. Okay, but this we know that this is iota, and gamma naught is basically the matrix which we introduced in the first video, and partial naught, of course, we know to be the time derivative plus iota, and this again we know to be the nester of the gamma matrices. Okay, and then this is just the spatial derivatives. Is that how you pronounce it? Okay, now what we are gonna do is we are gonna write down our spinner as kind of like two part and two part. Let me just write it. So you can write your spinner as phi and chi. Okay, where of course both phi and chi are two component spinners, what we call the upper and lower spinners. If you do that, then you can just check for yourself that in that case your Dirac equation, this applied to psi and phi, to phi and chi, gives you two coupled equations of motions. Okay, and those equations are, let me just go ahead and write them down. You can see it from here to those equations are partial t phi equals to minus iota the Pauli 3 vector sigma dot, this is the vector, okay, times the gradient of chi plus m phi. Okay, so this, as you can see, chi and phi are coupled. Okay, times, okay, just let me just go ahead and write it down again. Iota partial t chi is equals to minus iota sigma dot the gradient of phi minus m chi. So you can write the Dirac equation as two coupled differential equations too. Okay, and it's called the coupled two component form. Okay, and this is the first hint of a physical interpretation, and here the hint is that phi in this case is the particle while chi is the anti-particle. Okay, in the non-relativistic limit. Okay, and now what we are going to do is we are going to back our claim. Remember that the way that we derived the Dirac equation was by demanding that we want an equation which should be the square root of the Klein-Gordon equation. So let me just go ahead and prove that to you, that the Dirac equation in fact is the square root of the Klein-Gordon equation by simply multiplying it with itself and getting the Klein-Gordon equation. Okay, so I'm just going to do that, and let me just iota, this is the Dirac equation which we just derived. Okay, iota gamma mu partial mu minus m psi equals 0. So this is just me multiplying the Dirac equation with itself. and let's just go ahead and do that. So you get first of all you get minus iota squared, which is plus 1. So you get gamma mu partial nu okay, minus iota gamma nu partial nu m minus iota gamma mu partial mu m plus m squared into psi is equals to 0. Okay, so this is what you have so far, but this quantity okay is 0, right? Why? Because we know that let me just go ahead here pretty up. Yep, from here. Okay, due to this fact the quantity below is simply 0. So what we have here is gamma mu partial nu plus m squared into psi is equals to 0, right? But we know that we have seen that this thing, again from the first video, we defined it in such a way that this should be equal to partial mu, right? And we just simply put that back in and we get partial mu plus m squared to psi equals to 0. And that's your Klein-Gordon equation. So congratulations. Each component of psi satisfies the Klein-Gordon equation. So what you get again is what we claimed. Okay. Now you can go ahead and do a whole lot of things with this. For example, you can go ahead and show that the Dirac equation gives you a positive current and probability conservation and so on. Okay, but of course that is not needed for our project, so I'm just going to skip that. But again, you can just go ahead and prove that too. You can look it up, or you can look it up in a book or a ChatGPT or whatever is suitable for you. Okay, so also you can show that the Dirac equation is Lorentz invariant, okay, covariant as sometimes we call it. So you can show that too, but again we are not going to do that here.